Good morning, my name is Tommaso Corato and under the supervision of Professor José Suárez Ciedo Grande, I am presenting my dissertation for the defense of my thesis for the Master in Finance, titled A Genetic Algorithm Temporal Convolutional Neural Network for Stock Selection. The main scope of this thesis rests on the research on the ensemble model composed of a genetic algorithm and a temporal convolutional neural network. We will try to estimate the predictive power of this model. To the best of our knowledge, this is the first time these two models have been combined, at least in the stock market research. Why exactly do we choose this topic? Since the beginning of the stock market, the goal of everyone that has ever traded has been to predict the movement of the stock market and taking advantage of that prediction to make money. In the past few years, 56% of hedge funds have used AI or machine learning to inform their investment decision. Two-thirds said they use machine learning to generate trading ideas and optimize portfolios, and just over one quarter said they use automation to execute trades. This is the power and influence that machine learning has and will have in the future of finance, and the only way to be a step ahead of other investors that also use machine learning to trade is to have a better, faster, and more accurate stock picking algorithm. In this project, we will try to create an algorithm that can be sufficiently accurate and is able to make investment decisions accurate enough to outperform the market, both in the short and long term. What is our goal? The goal of this project rests on three main points. The main goal of the project is to build a temporal convolutional neural network that can predict in an accurate enough way the next day's swing of the market. Our secondary goal is to build a successful investment strategy and to identify which indicators are useful and which are not to predict stock prices. And finally, our tertiary goal will be to disprove the weak form of the efficient market hypothesis, proving that it is in fact possible to predict the price of the stock market using past data. The main system used in this thesis is called artificial neural network. But we can ask, what is an artificial neural network? An artificial neural network is a machine learning system inspired to the human brain that consists of an output and an input layer, and usually one or more hidden layers. These layers are formed of several connected nodes that we call neurons, so that together they model the neuron structure in a brain. Each connection can transmit a signal to the other neurons, resembling the synapses in a brain. An artificial neuron receives the signal, then processes it, and signals the neurons connected to it. When the hidden layers are more than one, like in our model, then we talk about deep neural networks, the fundamental structure of deep learning. But how does this machine learn? How does it work? The main learning mechanism is called backpropagation, where the initial output is compared to the desired output, and the weights in the system are adjusted until the difference between the two is minimized. The activation function instead has the role of deciding whether or not a neuron will be activated after taking the weighted sum of the inputs. The subtype of ANN that we use in this thesis is called convolutional neural net. What is the difference between an ANN and a CNN? Convolutional networks are inspired by biological processes. In fact, the connection between neurons is created to resemble the organization of the animal visual cortex. CNNs are a special kind of neural network for processing data that has a grid structure. Examples can be time series data that can be considered as a one-dimensional grid, and image data, which is of course a two-dimensional grid of pixels. Convolutional networks had an incredible success in the practical application, and are one of the main reasons why deep learning became so successful in the past decade. Named convolutional neural networks means that at least one layer of the network uses a mathematical operation called convolution that can be defined as the integral measuring how much two functions overlap as one passes over the other. Explained it easily, it can be seen as the way of mixing two functions by multiplying them. A CNN is a combination of two basic building blocks. First, the convolution block, a combination of convolution layers and pooling layers. This block performs the crucial task of extracting features from the data. And second, the fully connected block. There is a fully connected, simple neural network architecture. A convolutional layer has the task of convolving the inputs and pass its result to the next layer, or multiplying the value of a cell corresponding to a particular row and column in an input matrix, with the value of the corresponding cell in the filter matrix. A pooling layer has the task to reduce the spatial size of the representation so that the number of parameters and computation in the network are greatly reduced. But How does a convolutional neural network becomes a temporal convolutional neural network? First, using a 1D causal convolution, meaning that there is no information leakage from future to the past. And second, with the equal length sequence mapping, meaning that the architecture can take a sequence of any length and map it to an output sequence of the same length, just the same as a recurrent neural network. The optimization method that we use in this thesis to select which features to include in the final dataset is called genetic algorithm. A genetic algorithm is an optimization algorithm, part of the family of the evolutionary algorithms. The GA is based on the animal genome and follows an evolutionary strategy that brings the population to achieve an optimum. The basic components of a genetic algorithm are the genes, the chromosomes, and the population. A GA is a way for passing from one population of chromosomes, in our case strings of 1 and 0s, to a new population, using a process inspired by natural selection, joined with a crossover, mutation, and inversion operations, inspired by the genetic recombination of chromosomes. Each chromosome is made of genes, where each gene is a particular allele, in our case, a 1 or a 0, where a 0 deactivates a colon, and 1 activates one. But how does the GA make a choice? Makes a choice based on the fitness of each chromosome, that is a score based on certain metrics, in our case, the mean average square error. According to this matrix, the operator selects which chromosome in the population will be allowed to reproduce, with the fitter chromosomes having a higher probability of reproducing than the less fit ones. During the crossover, two chromosomes exchange subparts using a process that tries to simulate the biological recombination of two single chromosome organisms. The process of mutation randomly changes some of the allele values in the chromosome based on a given probability of mutation. In our case, a 0 becomes a 1 or vice versa. The inversion process instead reverses the order of a contiguous section of the chromosome, rearranging the order in which genes are arrayed. The project method. Let's discuss now how we built our project. What exactly did we use to produce the model to predict the stock prices? The data came from all the components of the Wilshire 5000 index for a total of over 3,600 companies. Each company had 87 features, and the whole dataset ended up having almost 60 million rows. We tracked the data from 1999 to 2019 with a daily frequency for a total of 21 years. The process that our model followed was first to feed the data to the GA, allowing it to select which features would have led to the minimum mean average percentage error. Then, after the GA selected the best set of features, we ran the normal TCN versus the optimized TCN to see if there had been some actual improvement. We ran a test both using statistical measures and performing a backtest to check how they would have performed in the market. We pause now to analyze the results of this thesis. First, we want to look at the metrics that we took into consideration when analyzing the performances of the TCN with the full dataset and the GA-TCN ensemble model. By looking at these variables, we can see that the mean square error of the TCN is actually lower than the mean square error of the GA-TCN. And also, the explained variance score of the TCN is slightly better than the GA-TCN. This would lead us to think that the TCN is actually a better model than the GA-TCN. But this is not true. In fact, these two variables are actually easily influenced by the magnitude of the data. So, a $1 error on a $1,000 stock is going to be worth as much as a $1 error on a $1 stock. But we know that when investing, these two things are not the same. In fact, one is a 0.1% error, the other one is a 100% error. So what we should look at is actually the mean percentage error, and in fact, is exactly the metrics that we optimized when using the GA genetic algorithm. When we're looking at the mean percentage error, the TCN has a 35.9% error, while the GA-TCN only at 27.58. We pass now to analyze more easily understandable results, like, for example, the results of the backtest. Here we have the returns of the backtest that has been performed from the 5th of May 2017, a date that has been chosen randomly, for 12 weeks. The TCN model, here indicated with full, gave us a 12% return, while the GA-TCN ensemble, here indicated with best, gave us actually a 17.5% return, while the index, our Wilshire 5000, only gave us a 3.3% return, meaning that the TCN overperformed by 8.5 and the GA-TCN by 14.1. But we can ask, how about the results weighted by their standard deviation? For this, we bring down the Sharpe ratio. Even when weighting with the Sharpe ratio, we can see how the GA-TCN is still overperforming the Wilshire 5000 that has a very low standard deviation, while the normal TCN is actually underperforming, meaning that we were able to bring the TCN to have a higher value per standard deviation. From the result that we have obtained from this research, we can conclude that there is some utility in using a genetic algorithm to optimize a TCN model. Nevertheless, some issues were present when we developed the project. The results, while promising, cannot be considered statistically significant yet. In fact, it would be necessary to run the GA-TCN versus the TCN versus the index for several different periods before we can actually give accurate conclusions. A possible solution could be to rerun the same 12 weeks test over different periods. The complexity and computational intensity of this project brought us to make certain simplifications in order to be able to run this model on the means and time at our disposal. These simplifications, though, might have created some problems that made the project less valid than what it was supposed to be. First and foremost, the computational intensity of the genetic algorithm made it impossible to run it over the whole dataset, forcing us to run the model only on 10% of the data. While 10% of the data selected at random should be still sufficiently statistically relevant, we cannot know what the result of the GA would have been if we had run it over the whole dataset. Secondly, there could be a case of data leakage when evaluating the performance of the GA-TCN and of the TCN, meaning that the performance of the optimized model was better because it had been optimized on the same data. In fact, the GA has been trained on the period 1999 to 2019, and the backtest took place in 2017, meaning that we know that the subset we had chosen was the best for the past, but we cannot say anything about the future. As a conclusion, we have some recommendation for eventual new experiment using the same concept, after fixing the issues present in the previous section. Firstly, it could be beneficial to use a genetic algorithm or some other form of optimization to choose the hyperparameters of the TCN, for example the number of layers and neurons. This would lead to a much more computationally intensive problem, but with greater means, it is probably feasible to complete it in a reasonable amount of time. Secondly, it would also be useful to find a way to optimize the numbers of genes and of generation that the GA should iterate over, so that it is possible to reach the best result without useless additional computations, and to find the best set of crossover, mutation, swap, and translation probabilities. Finally, despite some minor issues and the fact that the results are not definitely conclusive, the experiment gave promising results, and it seems that this approach could use some great results. In virtue of this fact, I believe that the project was a success and that both the genetic algorithm optimization and temporal convolutional neural net structure are worth exploring more in the field of stock prices prediction. With this, we have reached the conclusion of my thesis. I thank everyone very much for your attention. And a special thanks goes to my supervisor, Jose, that helped me throughout the development of the thesis, and that gave me a great opportunity of learning machine learning algorithms this summer during my internship. In case anyone is interested in the code of my model, you will find a link to my GitHub in the description down below. Thank you very much.